question 3 from that tutorial set was on multi-path, and then question 4 is on mobility, the Doppler effect. All right, so we have a terminal that's traveling at a speed of 80 kilometers per hour in a Rayleigh fading channel, receiving an RMS signal amplitude of 2 millivolts. And then we asked quite a few questions. Now, in short, the answers are pretty straightforward for these questions because the closed form expression or the equations are given in the lecture notes. So the important part here is for us to understand what they really mean, all right, and how does that affect the design of the system and then performance evaluation of the system, right? So let's try and understand this problem a bit better. So it says, question 4. So we have a mobile device that's traveling at a speed of 80 kilometers per hour. So that's obviously with respect to a base station that it's connected to. And the direction of the motion is not given here, right? So we can just say it's traveling in this direction. And it says it's a Rayleigh fading channel as well. That means that there's no line of sight. So that's a building there, let's say, for example. There's obstruction. And then the power received is probably something like that. And it says the RMS signal amplitude, so the root mean squared signal amplitude is 2 millivolt. So that's the that's RMS is 2. So that's what the power is received signal. That's 2. The root mean squared. Okay. And part A, you calculate the Doppler, or the maximum Doppler, Fm. It's pretty much the velocity times your frequency divided by your the speed of light. The velocity is given as 80 kilometers per hour. We just need to convert that into meters per second. Multiplied by the frequency, which is 90 megahertz. So F is given as 90 megahertz. So that's 90 into 10 to the 6 divided by 3 into 10 to the 8. So that's directly from the lecture notes. That's 6.67 hertz. I think we did this last week, so just for the sake of completion. Right. Part B. Find the level crossing rate NR for the signal to go below an amplitude of 0.1 millivolts. So if you look at this diagram here, this is a received signal, right? So this is how that I've drawn the received signal. That's the RMS. So if the signal were to go, so that's 2 millivolts here. So we do that. That's RMS equals 2. So that's that. And the threshold is Z equals 0.1 millivolts. obviously the signal will just go all over that way. Just trying to test it. So this is not in power, this is in receive signal amplitude or magnitude in millivolts, right? So part B, we need to calculate the level crossing rate, means that how often the signal, received signal, crosses the Z value here. Right? So that's the level crossing rate, the rate of it crosses. And for a Rayleigh channel, there's an expression given in the lecture notes that can be, that's proven, so which is given by square root of 2 pi Fm, which is what you calculated in part A, parameter called rho, we'll see what that is, exponential minus rho squared, e to the power minus rho squared, right? Where the value rho is given by your Z value on RRMS. So RRMS is the root mean squared value of the received signal amplitude, this one. And Z is the threshold that we are after, okay, in terms of the signal amplitude. That shouldn't go beyond, below. So that's the ratio here, rho. Now that you need, so rho is given to us, obviously 0.1 on 2. And then when you substitute for this, for square root of 2 pi, Fm is 6.67, 6.67, rho is 0.1 on 2, exponential minus 0.1 on 2 whole thing squared. That should give us a value of 0.83. So that's a level crossing rate for a Rayleigh channel for this particular scenario. So you can see that if the mobile terminal is moving faster, your Doppler will be higher, and therefore the rate of crossing that level will be also higher because it's proportional to Fm, right? Then part C, find the average fade duration. So fade duration is the amount of time in a period. So if you take a t period here, the amount of time the signal will be below is 0.1 millivolt. So if you want to calculate, you just calculate the amount of time that the signal falls below 0.1 or falls below the level Z, and then you add that up and then divide it by the total time period. Right? So that's the fade duration, average fade duration. And for a Rayleigh fading channel, it has got a, again, it's got a nice expression, so don't mix up between my rho and E. It's better. E to the power rho squared minus 1 divided by square root of 2 pi Fm rho. This is an E exponential, and this is a rho, right? E to the power of rho squared. This is a rho. So again, we got all the parameters. Rho is 0.112, Fm calculated, and then we just need to substitute values. And we've got to substitute values there, so just write the answer there. So for this particular case, on average of 3 milliseconds, is the average fade duration. part D, now this is the coherence time. The coherence time, we said that so again, going back to the two main causes of small scale fading, Doppler and multipath fading, right? So the multipath fading effects leads to a key parameter called coherence bandwidth, right? That's the bandwidth where the signal is highly correlated, and if you transmit a signal within that bandwidth, very likely or highly likely you will receive the same signal with a high amount of correlation, right? Likewise, in the when we have a mobile environment or high mobility environment, the Doppler effect leads to a key parameter called coherence time. That's the amount of time where the channel remains highly correlated, or in other words, the same. Right? So that's the time that we are going to calculate, the coherence time TC. It's an approximation, but it's given by 16 pi Fn. So that's inversely proportional to the Doppler. In a zero Doppler environment, the channel doesn't change. Right? So that's what it means. So if you substitute for values there for Fm, it's 6.67. You should get a coherence time of 27 milliseconds.
Is that 9? Is that 9, right?
Sorry?
No. Is that 9? The time correct?
Sorry, I can't hear you.
TC is equal 9, right?
TC is equal to 9 on 65. Yeah. Correct. So then part E, based on the value of this coherence time TC, we can relatively classify a wireless channel, whether it's a fast fading channel or a slow fading channel, right? So how do we make that let's say classification is by comparing to the symbol duration. We transmit symbols by symbols, right? A symbol consists of multiple bits, right? So depending on how long the symbol is, and we compare that, we compare the coherence time to a symbol, and then we say that we classify that it's a fast fading channel or a slow fading channel. So if the channel is changing faster than the symbol period, then it's a fast fading channel. In other words, if your coherence time is smaller than the symbol period, then it's a fast fading channel. It's fading faster than the symbol period, right? So if it's the other way around, if the coherence time is larger than the symbol period, it's a slow fading channel. In other words, in a slow fading channel, the channel variation per symbol is not much. In a fast fading channel, over a symbol period, the channel can undergo variations. So when you recover the data, when you estimate the symbol and recover the information, that is really crucial. The amount of complexity that needs to go into the receiver. Okay. So here, so that relates to part E. We now ask, from part D, the bit rate of 20 kilobits per second. So the bit rate is 20 kilobits per second. Is used. What type of channel with the transmission experience? Whether it's a slow fading or a fast fading. So this gives us a bit duration of 1 on RB, which is 0.05 milliseconds. And therefore, since TB is less than TC. So this is less than TC, right? It's a slow fading channel. So if you look at the diagram, we have, so bits transmitted. That's the bit duration. The bit duration here is what, 0.05 millisecond. That duration is dB. And then your channel coherence time is somewhere around here, this much, TC. So it's a slow fading channel. So this is your understanding. So this is what you need to understand from this problem. So small scale fading, again, to quickly summarize, two main causes, mobility leading to Doppler, and hence we have a resulting coherence time of the channel. And the second cause is multipath effect, leading to coherence bandwidth of the channel that affects the bandwidth of the signal that will be transmitted. All right. Now that completes or concludes propagation effects, channel effects, or in wireless communication, right? So now we're going to move on to actual communication. So far we've been talking about the environment, the propagation effects, and how to quantify, classify wireless channels, and understand how propagation works, and so on. Right? Now we're going to talk about transmission, signal transmission and reception. So that takes us to week 5 tutorial set. So